Okay, on your test for this unit, there is one large problem that deals with pretty much everything that we've talked about in projectile motion. This is exactly that problem using the exact same values and the exact same questions. So if you follow along carefully, you should be able to do this without problem the day of your exam. Okay, so in this problem, we have Mr. Fleming test launching his homemade potato launcher on the roof of his apartment building that is 65 meters above the ground. On one particular test launch, he fires a potato at an angle of 40 degrees above the horizontal with a resultant velocity of 28 meters per second. Accidentally, he hits a police cruiser on the street below. And I wouldn't be so sure that that was an accident. But in any case, we have 4 problems that we need to solve within this. We want to know the highest point of the potato's trajectory, that is right there. It's not going to be 65 meters, obviously, because everything below here is 65 meters. We'd love to find this distance right there so that we can add it to the 65 meters. Question B says, what is the total time in flight for the potato from launch to impact? Well, this is going to be a little more difficult to understand than what we've been doing up until this point. But here's how we're going to do it. We're going to break this trajectory down into 3 parts: A, B, and then C. Now I want you to realize B is not halfway. Halfway actually occurs somewhere around here. But what we'd like to find is the property of this projectile up until that point, and then we're going to analyze it from B down to C. A couple of things we know, like the velocity in the vertical direction at that point, and we also know that the time it takes to go along this path from B to C would be the same time it would take to fall from B directly down to the ground. So we're going to use that to our advantage. If we can find the time that it takes to go from A to B, and then find the time that it takes to go from B to C, then if we add those 2 together, then we can find our total time. Question C wants to know, how far from the base of the cliff does the potato land? Well, in order to do this, let's get rid of all this. In order to find that, you need to realize something very, very simple. This is in fact probably the easiest one of these questions. Whatever we find for our velocity in the x direction, it will keep moving at that velocity the entire way down. It will not change. So once we found the total time that we're in the air, that is from part B, then we will know that all we would have to do is multiply that time by the velocity in the horizontal direction, and then we can find how far it is in the horizontal direction away from the base of the building. And then the last question wants to know, with what resultant velocity does the potato make impact with the police cruiser? Remember, resultant means it is a combination of some horizontal and some vertical components, the resultant of which is drawn from the tail of the first to the tip of the last. So, in other words, if we know this value, and if we know this final value in the vertical direction, then we can solve for this guy right here using the Pythagorean theorem. It's the same way we've done it. Okay, so we'll start with part A. Okay, well, the very first thing that we have to do is we realize that if we're given this resultant vector, we need to break it up into its horizontal and its vertical components. So realize that there is this horizontal component and this vertical component of the resultant velocity. We're going to break that down in the same way that we have. To find the horizontal component, the back of your reference table says to take the resultant and multiply it by the cosine of the angle it makes for the horizontal. And to find the vertical component, the initial vertical component, because this will be changing as a result of gravity affecting it. The vertical component is the resultant times the sine of the angle that it makes for the horizontal. If you plug in 28 meters per second for the resultant in both cases, and if you plug in 40 degrees as the angle in both cases, then you should find that your horizontal component ends up being 21.4 meters per second, and that will remain a constant because remember, there is no acceleration if we neglect air resistance for this problem. There is no acceleration side to side. And for your vertical component, you should find that its value is, if you round up, it's pretty damn close to being 18 meters per second. And that it's in the vertical direction. This will start out at 18 meters per second, and at the apex, it will reach a 0, and then it will get faster and faster. Now, you're used to this returning back to level ground, where its final velocity was the same as the initial, but just with a different direction. In this case, it won't be reaching the same level. It will be going even further. So you need to realize that this is just your initial vertical velocity, and this is your horizontal component. This will change, and this will stay the same. You also need to realize that because you are moving in the upward vertical direction and in the downward vertical direction, that you must call one direction positive. And if anything is pointing up, it is positive, and you must call anything pointing down negative. Somewhere on your paper you should start a menu of things that you know that are in the horizontal and in the vertical direction. This menu is going to be a little bit more than what we're used to, only because of the fact that we have 3 segments, A, B, and C. But I will get into that in just a moment. For now, just set up your menu with the usual suspects that you would put in, like velocity in the horizontal direction, and displacement in the horizontal direction, and initial velocity in the vertical direction, and your acceleration in the vertical direction. Remember, time is key, so I'm going to put him at the bottom of my menu. But there are other items that are going to go on in this menu. For example, the final velocity in the y direction, or maybe even the velocity at the apex in the y direction, at the very, very top. So these are items that we'll need to consider. And the fact that we just found those components means that we can throw in their values right now. So the velocity in the horizontal direction will be 21.4 meters per second. Include the units. I do not know my horizontal distance. I do know my vertical initial velocity is 18 meters per second. I also know my velocity at the apex, at the very top of the trajectory. It's going to be 0 meters per second. I know that my acceleration due to gravity is a negative 9.8 meters per second squared. Again, it's negative because I go up and down, and gravity is always pointed down, so as a result it will be negative. The final velocity in the vertical direction, I do not know. If we landed at the same height, I could just say it was negative 18 meters per second, but we don't, so I can't, and I won't. And the time for this thing to be in the air is unknown. And it turns out we're also going to add other items to our menu, specifically that relate to time. And here's what I suggest you do. Leave some room for the following. Time from A to B, that is from where it starts to its highest point at the apex, and time from B to C, that is its apex and the time it takes to hit the ground. Okay, so for this first problem, we're set. With respect to ground, what is the highest point of the potato's trajectory? In other words, it wants to know, what is this height? Well, if you look at your menu, you know that the vertical velocity at this point, at its apex, is 0 meters per second. You also know that its initial velocity at this point was 18 meters per second. The key to solving this problem is to realize that, like I said, we have 3 segments here, from A to B, and then from B all the way down to C. Just looking from A to B, if you were to write a menu of things that you know from A to B, you could use this equation, the one that looks familiar, of VF squared is equal to VI squared plus 2AD. But I'm going to rewrite that with the names for things that actually apply to this case. So instead of final velocity, I'm going to say velocity in the y direction at the apex squared is equal to the initial velocity in the y direction squared plus 2 times the acceleration in the y direction times the displacement above the roof. So maybe I'll say from A to B. This is going to help me find this total, because once I've found this little distance, I can add it to the height that I am above the ground, and I will have the total height above the ground. So first let me get this guy alone. What I need to do is subtract VIY squared from both sides. And now I'll end up having something that looks like this. VY at the apex squared minus VIY squared is equal to 2AD, because this whole term goes away. But if I want to get displacement alone, I'm going to divide both sides by 2A. And now I'm left with the height above the roof, or in this case the distance from A to B, this guy right here. If you plug in your numbers, it should look like, well, let me give myself some room. So plugging in my numbers, for my velocity at the apex, it's 0 meters per second, the whole thing squared, minus the initial velocity, which was 18 meters per second, the whole thing squared, divided by 2 times the acceleration due to gravity. Well, that's 2 times a negative 9.8 meters per second squared. So 18 squared divided by what would be negative 19.6 gives me a value of 16.5 meters. And this is the value of the height above the roof. Notice the negative divided by a negative gives me a positive displacement in the upward direction. Now, at this point, if I'm 16.5 meters above the roof, then my total displacement, or total displacement in the y direction, would be equal to the 16.5 meters above the roof plus the 65 meters that I am above the ground, which would give me 81.5 meters above the ground. This is my highest point with respect to the ground. Okay, moving on to part B. Well, before we do that, I want you to see how our menu has updated, the things that we know. Again, we have the velocity in the x direction, we've known that, as well as the initial velocity in the vertical direction, and the acceleration in the vertical direction, and the velocity at the apex, again, which is right there in the vertical direction. But we've also found the height that we are above the roof. We could call that the distance from A to B, if I label my points, A, B, and C. And then we also know the maximum height of this thing, which is the distance from B to C. And now we're asked in part B, what is the total time of flight for the potato from launch to impact? Now there are a few different ways to do this, but for our level, I think the easiest way is to analyze the time of flight from A to B, and then to analyze the time of flight from B to C. So we will do that, and it will look like this. The time from A to B plus the time from B to C. Now I want you to realize that the time from A to B is going to be given with this equation. It'll take some time to realize it, but I'm going to tell you it now. We know in the vertical direction, if we were to think Vy equals Vi, Vf rather equals Vi plus At, well, we want to know the final velocity at the apex. So our initial velocity in the y direction plus the acceleration in the vertical direction times the time will give me the time from A to B. That is, our initial velocity here was 18 meters per second. Our final velocity right there was 0 meters per second. So we're just pretending we're going from A to B to find this time. Do I know the value for my velocity at the apex? Yes, I do. It's 0 meters per second. Do I know my initial velocity in the y? Yes, I do. Do I know my acceleration in the vertical direction? Yes, I do. I can throw all these in and solve for t, time, from A to B, and it ends up looking like this. The time from A to B is equal to the velocity in the y direction at the apex minus the initial velocity in the y direction divided by the acceleration due to gravity. In other words, the time from A to B is equal to 0 meters per second minus 18 meters per second divided by a negative 9.8 meters per second squared. Run those numbers through your calculator, and you should get that the time it takes to go from A to B is 1.84 seconds. I won't put a square around that because I'm not done. It's just 1.84 seconds to go from A to B. So 1.84 seconds. Now, I need to find, well, before I go on, I want to just stop here for a moment. I want you to realize that I used this equation because I was trying to find time. I could have also used the equation to give me time where I have distance equals VIT plus 1/2 AT squared. But I want you to realize why I'm not going to use that. And it's because my initial velocity is not 0, which means this whole thing does not cancel out. And if I try to plug in for this and for that and for that to find time, I won't, because I have t and t squared. To solve this equation, you would need to use what's called the quadratic formula, and that's beyond the scope of our class. So I choose an equation like this that only gives me one unknown along with 3 known values, and then I solve to get it alone, and it looks like this. And then I plug in my values to get that. So now I want to find the time that it takes to go from here at B all the way down to this point at C. Well, let me clear out some space. And I want you to realize that the time it takes to go from B to C along that path of trajectory is the same time that it would take if you were just to drop the potato from B and let it fall all the way down to the ground. So, a little more space. Here's how we're going to find that. Instead of using the equation that we use for time from A to B, I would like to find the time from B to C with this equation. Distance in the vertical direction is equal to the initial velocity in the vertical direction times the time plus 1/2 AT squared. Now you might be thinking, wait, I thought you said our initial velocity is not 0. Well, let me rewrite this equation in terms of what I'm going to be using it from. The distance from B to C is equal to my velocity at this point, which is at the apex. The velocity at the apex times the time from B to C plus 1/2 the acceleration due to gravity times the time from B to C squared. Well, in this case, my initial velocity is 0 because I'm starting at this point. So this whole entire term goes away, which ends up being really convenient for us, because now we're just left with the distance from B to C in the vertical direction is equal to 1/2 AT from B to C squared. So I'm going to solve to get t all alone by itself. To do that, I will divide both sides by 1/2 the acceleration, and then I will take the square root of both sides. So that now my equation looks like this. The time from B to C is equal to the square root of d over 1/2 A. Throwing in the stuff that I know, from point B, it looks like the total height above the ground, which is 81.5 meters, divided by 1/2 the acceleration due to gravity, which is a negative 9.8 meters per second, and half of that. And then you say, wait, I have a negative under the radical. Well, before you get crazy, I would like you to realize that this 81.5 is a negative displacement, because now you're going from B down to C. And remember, anytime anything is down in this case, we're going to call it negative. So what is the square root of a negative 81.5 divided by a negative 1/2 9.8? Well, if you take the square root of that, you should get a value of 4.07 seconds. And that is the time it takes to go from B to C. From B to C. Well, if it took 1.84 seconds for the first part, and then we found it took another 4.07 seconds for the second part, then the total time that it would take over here, the total time that it would take would be 5.92 seconds for the entire trip. Moving on to part C, take a look at our menu, and we've added the total time and all the other values that we've had. I like part C, and here's why. It's easy. How far away from the base of the building is the police cruiser when it gets duffed? Well, let's take a look at the police cruiser down here. We are talking about this displacement in the horizontal direction. So, what we will do, let me adjust my screen. What we will do is simply realize that velocity in the horizontal direction is equal to displacement in the horizontal direction divided by the time. Well, this time is the total time, because my velocity in the horizontal direction will maintain the same speed the entire way down. So, because it stays constant, I will not use any equation that deals with acceleration. This is it. I know you, and I know you, and I'm trying to find you. Multiply both sides by time, it cancels out, and then you get an equation that looks like this. Horizontal velocity times the total time is equal to the displacement in the horizontal direction, or in this case, it is 21.4 meters per second times the total time of 5.92 seconds. And you get a total displacement from the base of the building of 126.7 meters. This last problem wants to know the resultant velocity that the potato hits the police car with. And I'm okay with D too. It's not as easy as part C, but it's still okay. It's doable. Remember, the resultant velocity is talking about the velocity that this potato has at the moment that it makes impact with the police cruiser. So in other words, we're talking about the resultant from the tail of the horizontal component to the tip of the vertical component when it hits that police cruiser. Whoa, relax. So if I could use those values, my horizontal and my vertical velocity, then I can find the resultant by just using the Pythagorean theorem. I happen to know that my horizontal velocity remains a constant 21.4 meters per second. My final velocity, though, when I hit the police cruiser in the vertical direction is not known. But I do know an equation that I can use to solve for it. The initial velocity in the vertical direction plus the acceleration in the vertical times the time total for this entire trip will give me that vertical component. In other words, 18 meters per second plus a 9.8 meters per second times 5.92 seconds in the air gives me a final vertical velocity of negative 40 meters per second. So now that I know the value of my vertical component, I can find the result by using the Pythagorean theorem. So, let me move this guy up there. And it turns out that if you want to find this resultant, it looks like this. A squared plus B squared is equal to C squared, or in our case, the horizontal component squared plus the final vertical component squared is equal to the resultant squared, or the square root of everything on this side is equal to the resultant. So I'm going to plug in my numbers, and it turns out the horizontal component squared plus the vertical component squared. Take the square root, and you find that the resultant velocity is equal to 45.4 meters per second. That is the magnitude of the resultant velocity. And then if I want to find its angle below the horizontal, well, that's as simple as taking the opposite over the adjacent and finding the second function tangent of that, the inverse tangent. So the inverse tangent of 40 negative divided by 21.4 If I take the inverse, the second function tangent of that in my calculator, I find that it is about 62 degrees below the horizontal. So my final answer for this resultant velocity that it hits the cop car with is 45.4 meters per second at an angle of 62 degrees below the horizontal. And that is the entire problem.